Hey everyone, get ready because we're diving deep today into the quantum realm. It's a world that really makes you rethink everything you thought you knew about how things work. We're talking particles acting like waves, uncertainty ruling the game, and reality itself kind of feeling like a mirage. And to guide us through this crazy universe, we've got Jürgo Schneppat's essay, Grundkonzepte der Quantenmechanik. It's like our map to the core principles of quantum mechanics, those principles that shook the world of physics over 100 years ago.
It's really wild. Just over a century ago, physicists were wrestling with these phenomena. They just couldn't explain them with classical physics. It was a huge shift in thinking.
It was like physics was getting a complete makeover. Schneppat takes us back to that time, the late 19th and early 20th centuries. Classical physics, with its neat and tidy laws, was hitting some major roadblocks. Things like black-body radiation. You know, the way hot objects give off light. It just didn't fit with what they thought they knew.
It's like the universe was trying to tell them something. But they weren't quite getting the message. Like with black-body radiation, classical physics said the intensity of light from a hot object should just keep increasing forever as the wavelengths get shorter. But experiments showed something totally different.
It was like the universe was messing with them.
Exactly. And then in 1900, Max Planck steps onto the scene. And he says, what if energy doesn't flow smoothly? What if it comes in these little packets? Quanta. It was a radical idea. It went against everything classical physics was about.
Like instead of a ramp, energy's hopping up and down stairs.
Wild, right?
But it was the key to figuring out black-body radiation.
And that was just the start. 5 years later, Albert Einstein takes this idea of quantized energy and uses it to crack the photoelectric effect. That's where light shining on metal knocks electrons loose. Einstein said light wasn't just a wave, it was also a stream of particles, photons, each carrying a quantum of energy.
So light's got this split personality, wave and particle, this wave-particle duality. It's one of the craziest things in quantum mechanics.
And Schneppat illustrates it perfectly with the double-slit experiment. Picture this. You're shooting electrons, those tiny particles and atoms, at a barrier with two slits in it.
Okay, I'm seeing it. Now, in the normal world, you'd think the electrons would go through one slit or the other, making two separate bands on a screen behind the barrier. But that's not what happens in quantum land, is it?
Nope, not at all. Instead of two bands, you get an interference pattern on the screen, like you'd see with waves. It's like each electron is going through both slits at the same time, interfering with itself to make this pattern.
Wait, so an electron can be in two places at once?
Yeah.
That's mind-blowing. But here's what really gets me. If you try to measure which slit the electron goes through, the interference pattern vanishes. It's like watching forces the electron to choose a path. Like it's saying, okay, fine, I'll be a particle.
Now things are getting really interesting. It seems like measuring something actually changes it. Schneppat dives into the Copenhagen interpretation here. It suggests that before we measure a quantum system, it's in a superposition of states, meaning it's in all those states at once. But when we measure it, the wave function, which is the mathematical description of the system, collapses, and we see just one outcome.
It makes you wonder what reality even is. What does it mean for something to be in multiple states at once until we look? And that takes us to another pillar of quantum mechanics, Heisenberg's uncertainty principle.
This principle from Werner Heisenberg says there's a limit. We can't know both the position and momentum of a particle perfectly at the same time. The more we nail down one, the fuzzier the other gets. And it's not just our instruments, it's a fundamental limit in the universe.
So uncertainty is baked into reality itself. It's not that we can't measure things accurately enough, it's that they're fundamentally fuzzy. That's a huge shift from the clockwork world of classical physics.
Huge. And this uncertainty isn't just theoretical, it has real consequences. It's why electrons don't just spiral into the nucleus of an atom. The uncertainty in their position and momentum keeps them from collapsing.
So the uncertainty principle is what gives atoms their structure and stability. And that brings us to another key principle Schneppat highlights, one that's all about how matter is organized, the Pauli exclusion principle.
This one, by Wolfgang Pauli, says no two fermions. Things like electrons can't be in the same quantum state at the same time. It's like a cosmic rule. No two fermions can have the same address.
Like a cosmic game of musical chairs. Each electron needs its own seat.
Exactly. And this simple rule has huge implications. It explains why atoms are structured the way they are. Electrons in shells around the nucleus. It's why we have the periodic table, and why different elements have different properties.
It's amazing how this abstract principle shapes the world around us. And finally, Schneppat reminds us of quantization. The idea that energy comes in these separate packets, like rungs on a ladder, not a smooth, continuous flow.
This idea from Max Planck is at the heart of quantum mechanics. It explains why electrons in an atom can only be at certain energy levels, not in between. They can jump between levels by absorbing or emitting photons with specific energies. And that's what gives us things like atomic spectra and lasers.
So quantization isn't just some abstract idea. It's why we see color and have lasers. Schneppat really lays the groundwork for understanding how quantum mechanics changed everything, wouldn't you say?
Absolutely. He shows how these strange counterintuitive principles, wave-particle duality, the uncertainty principle, the Pauli exclusion principle, and quantization, they're the cornerstones of quantum mechanics. And we're just getting started. Welcome back. We're picking up where we left off with Jörg Schneppet's Grundkonzepte der Quantenmechanik. He introduced us to wave-particle duality, the uncertainty principle, and the idea that energy itself is like on a staircase, not a smooth ramp.
It's definitely a lot to process.
Yeah.
But Schneppet keeps going. He brings in the wave function. It's like the mathematical core of quantum mechanics.
It's super powerful, but also easily misunderstood. It doesn't pinpoint a particle's location or its momentum. Instead, it's all about the chances of finding a particle in different states.
So it's less like a map and more like a forecast.
That's a good analogy. Schneppat makes it clear the wave function itself isn't something you can physically see or touch. It's when you square its absolute value that you get the probability.
Yeah.
The probability of finding a particle somewhere, or with a certain momentum, or any other property you're measuring.
So it's all about possibilities, not guarantees.
Yeah.
Like reality at the quantum level is fuzzy, uncertain.
And to figure out how these probabilities change over time, we have the Schrödinger equation, named after Erwin Schrödinger. It's like Newton's laws of motion. But for the quantum world, it tells us how the wave function evolves, how those probabilities shift.
Schneppat mentions that this leads to some deep questions about what's real and the role of observation.
Exactly. And that's where the Copenhagen interpretation comes in. The most popular but still debated view of quantum mechanics. It says that before we measure a quantum system, it's in a superposition of states, meaning it's in all those states at once.
So only when we measure it does the system pick a state, and the wave function collapses. It's like our observation forces the quantum world to choose, to become definite.
Like we're bringing a specific reality into being by looking? Of course, this has sparked tons of debate about consciousness and the role of the observer. But no matter how you interpret it, the evidence for superposition and wave function collapse is solid.
So measurement is crucial in the quantum world. And speaking of mind-blowing concepts, let's tackle entanglement, what Schneppat calls spooky action at a distance. This is where quantum mechanics gets really weird.
Entanglement is one of those things that's super counterintuitive, yet it's been proven again and again. It happens when two or more particles get so linked that their fates are tied together, no matter how far apart they are.
So if we've got two entangled particles, and we measure one, we instantly know about the other, even if they're light years away.
That's the gist. But it's not like information is traveling faster than light. It's not a signal. Instead, think of the two particles as one system, even when they're physically separated.
Like two sides of the same quantum coin.
Precisely. If you flip a coin and see heads, you know the other side is tails without even looking. Entangled particles are like that. They share a single state. Measuring one tells you about the other instantly. It's like they have this unseen connection that goes beyond space and time.
Makes your head spin, right? And Schneppat points out entanglement isn't just theoretical. It's got real-world uses, especially in quantum information and communication.
Totally. Quantum cryptography is one exciting example. It could completely change secure communication. Imagine a world where eavesdropping is impossible, because any attempt to intercept a message would change the entangled state and reveal the intruder.
So unbreakable codes, thanks to the weirdness of entanglement.
That's the idea. And entanglement is also key for other quantum technologies, like quantum computing, which could solve problems that are way beyond classical computers.
We've covered a lot. Wave functions, the Copenhagen interpretation, and entanglement. Schneppat throws us right into the deep end, doesn't
He
it?
does, and there's more to come.
We're back for the final part of our quantum journey. And what a journey it's been. We've been exploring the bizarre world of quantum mechanics with Jörg Schneppat's Grundkonzepte der Quantenmechanik as our guide. We've encountered wave functions that are all about probabilities, the Copenhagen interpretation where observation shapes reality, and entanglement where particles are connected across vast distances.
Schnepp has really given us a taste of the strangeness and beauty of it all. But he also hints at something deeper, something that really makes you think.
I know what you mean. This whole deep dive has made me question what reality even is. If particles can be in multiple states at once, if observing something can change it, if particles can be linked across the universe, what does that say about the nature of our universe?
It suggests that reality might be way more subtle and interconnected than we ever thought. Schnepp brings up quantum tunneling, a phenomenon that really blurs the lines between possible and impossible in the classical world.
Right. It's like that scene in a movie where someone walks through a wall. I remember reading about it in Schneppet's essay. It's the idea that a particle can pass through an energy barrier, even if it doesn't have enough energy to go over it.
Exactly. Classically, that'd be a no-go. But in the quantum world, it's all about probability. The particle's wave function has a chance of extending beyond the barrier, even if the particle's energy is too low.
So there's a possibility, however tiny, that the particle can tunnel through and puck out on the other side.
It's not magic, but it sure seems like it, and Schnepp points out that tunneling is happening all around us. It's crucial for nuclear fusion, the process that powers the sun. Without tunneling, the sun wouldn't shine.
It's mind-blowing how these quantum phenomena are at work in the universe. And Schnepp throws in a few other fascinating tidbits. He talks about operators in quantum mechanics, these mathematical tools that represent physical quantities, like energy and momentum.
He also touches on the importance of spin. It's like an internal angular momentum for particles, something with no equivalent in classical physics. And it's key for how particles interact with each other and with magnetic fields.
And then there's symmetry and symmetry breaking,
Yeah.
which are fundamental for understanding particle interactions and properties at the deepest level.
Schnepp's essay has been an incredible journey. It's shown us the strangeness, the beauty, and the depth of the quantum world, a world where our everyday intuitions don't apply, where uncertainty and probability are the rules of the game, and where observation itself seems to play a role.
It's been mind-expanding, to say the least. Jörg Schnepp's Grundkonzepte der Quantenmechanik has been a fantastic guide, leading us through the core principles of quantum mechanics, and leaving us with even more questions than answers, which is the mark of a truly great exploration, wouldn't you say?
Absolutely. It reminds us that there's always more to learn and discover, and that the universe is full of wonders and mysteries beyond our wildest imagination.
So to all our listeners out there, keep exploring, keep questioning, and keep your minds open to the endless possibilities of the quantum realm. Thanks for joining us on this deep dive.